When you look up into the night sky, you can't miss it. That familiar W shape, a celestial landmark that has guided humanity for millennia. This is the constellation Cassiopeia. But what I want to show you is that this simple pattern is actually a gateway, a window into one of the most dynamic laboratories in our galaxy. It's a place where we can witness the birth of stars, the violent death of others, and maybe, just maybe, find a system that looks an awful lot like our own. It sounds like the beginning of a riddle, doesn't it? What could possibly connect an ancient queen's vanity, the explosive end of a star's life, and our modern search for extraterrestrial intelligence? Well, they all converge in this one patch of sky. Cassiopeia isn't just a random assortment of lights. It's a cosmic crossroads where ancient mythology and cutting-edge astrophysics meet. So, before we dive into these specific phenomena within Cassiopeia, we first need to establish its fundamental parameters. Let's get our bearings and understand its scale and its place in our celestial sphere. To begin, Cassiopeia covers a substantial area of our sky, nearly 600 square degrees. Now, to put that number into perspective, that ranks it as the 25th largest of the 88 officially recognized constellations. This is a significant piece of celestial real estate, a vast canvas for the objects we're about to explore. And on that canvas, even without any optical aid, a keen observer under dark skies could discern about 90 individual stars. That iconic W that we all recognize is really just the brightest, most prominent part of a much larger, more populated stellar neighborhood. It is, in essence, the tip of the iceberg. Now, your specific geographic location dictates your view of Cassiopeia. For observers in the mid to high northern latitudes, say North America or Europe, it's what we call circumpolar. It never sets below the horizon, it simply rotates around the North Star throughout the year. As you travel south, it appears lower in the sky until it vanishes entirely for observers in the far southern hemisphere. For those of us in the north, the optimal viewing window is during the autumn months, when it reaches its highest point in the sky. All right, let's now turn our attention to the 5 stars that form that famous W asterism. From our vantage point on Earth, they appear as a cohesive group, but in physical reality, they are fundamentally different stellar objects, each with a unique astrophysical profile. Let's break them down. First, we have Shadar, an orange giant star already in its final evolutionary stages, shining with a luminosity of 670 of our suns. Then there's Calf, a subgiant caught in the transitional phase between its stable main sequence life and its future as a red giant. Perhaps the most extreme of the group is Navi. This star rotates at an incredible velocity, over 300 kilometers per second, so fast that it's actively shedding mass from its equator into a surrounding gaseous disk. Rukba isn't a single star at all, but an eclipsing binary system, where 2 stars orbit each other, causing their total brightness to dim periodically from our line of sight. And finally, there's Seganin, a massive, intensely hot blue-white giant, radiating its energy from a distance of 440 light-years. Now, hidden among these giants and exotic stellar objects is a far more modest system, one that doesn't immediately draw attention. But this system, known as Eta Cassiopeiae, or Achird, might just be one of the most compelling targets in the search for extraterrestrial intelligence, SETI, precisely because of how familiar it looks. Achird is a binary star system, and in astronomical terms, it's a very close neighbor, situated just 19.4 light-years away. It's composed of a primary star, Achird A, and a smaller, cooler companion, Achird B. But the focus of intense scientific interest is that primary star, Achird A. Why? Because Achird A is, for all intents and purposes, a solar twin. It's the same spectral class as our Sun, a G-type yellow dwarf, and possesses nearly identical mass, surface temperature, and luminosity. If you were to hypothetically swap our Sun for Achird A, the change would be almost imperceptible. This striking similarity is what makes the system a prime target for astrobiological research. So, what makes this system such a compelling candidate for harboring life? It satisfies several key criteria. First, gravitational stability. The 2 stars are separated by a wide margin, which means the companion star's gravity is unlikely to disrupt the stable orbits of any planets in the primary's habitable zone. Second, age.
The system is approximately 5.4 billion years old. That's 800 million years older than our own solar system, providing a significant amount of extra time for life to potentially evolve. Third, it has sufficient metallicity, the heavy elements required for the formation of terrestrial, rocky planets. And finally, as a stable G-class star, it provides a clement radiation environment, free from the violent atmosphere-stripping flares that are common to more volatile star types, like red dwarfs.
So while Cassiopeia may host a potentially stable haven for life, it is also simultaneously a stage for extreme cosmic creation and destruction. Within this same constellation, we can observe both the stellar nurseries where stars are formed and the chaotic remnants of stars that have died. Take, for example, the Heart and Soul nebulae. These are immense emission nebulae, vast clouds of ionized hydrogen gas. You can think of them as stellar crucibles on a galactic scale. Deep within these glowing structures, gravity is actively collapsing dense pockets of gas and dust, forming protostars, new suns that are just beginning to ignite and shine for the first time.
And from the cradle of creation, we turn to the grave. This is Cassiopeiae. What you're seeing are these shredded remains of a massive star that underwent a core collapse supernova. The event itself, which occurred around the year 1667, was likely obscured from Earth by interstellar dust. But its remnant is a spectacular laboratory for astrophysicists. Today, this expanding shell of ejected material is the strongest extrasolar radio source in our sky, an invaluable object for studying the physics of one of the universe's most energetic events. A century before that explosion, Cassiopeia was the site of another, even more pivotal event. In 1572, the astronomer Tycho Brahe recorded the appearance of a stellanova, a new star, that suddenly became brighter than the planet Venus. His meticulous observations of its subsequent fading directly contradicted the prevailing Aristotelian doctrine of a perfect, unchanging celestial sphere. This event, now understood to be a Type Ia supernova, was a crucial piece of evidence that helped catalyze the scientific revolution, proving that the cosmos was not static, but a dynamic, evolving system.
But long before we understood supernovae or solar twins, ancient civilizations looked at these same stars and saw something else entirely. They saw a narrative. Let's now examine the Greco-Roman myth that gives the constellation its name, a classic cautionary tale about hubris. The myth revolves around Queen Cassiopeia's boast that her beauty exceeded that of the Nereids, the divine sea nymphs. This act of hubris angered the sea god Poseidon, who sent a monster, Cetus, to devastate her kingdom. An oracle declared that the only way to appease the god was to sacrifice her daughter, Andromeda. Andromeda was chained to a rock, but was ultimately rescued by the hero Perseus. However, Cassiopeia herself was not absolved. For her arrogance, Poseidon placed her in the heavens, eternally bound to her throne. And as the night sky rotates, she is condemned to spend half of each cycle hanging upside down, an undignified and perpetual punishment for her vanity. So after exploring its scientific and mythological significance, you're likely interested in locating Cassiopeia in the night sky for yourself. Fortunately, it's quite straightforward, using a simple navigational technique known as star hopping.
First, you need to find the Big Dipper. Identify the star Alioth. That's the third star in the handle counting from the bowl. Next, trace an imaginary line from Alioth directly through Polaris, our North Star. If you continue extending that line for approximately the same distance on the other side of Polaris, your line of sight will terminate directly on the unmistakable W formation of Cassiopeia. This method works reliably year-round for any observer in the Northern Hemisphere.
And so, Cassiopeia is far more than a mere pattern of stars. It functions as a bridge, connecting the myths of our ancestors to the most profound scientific questions of our future. It serves as a powerful reminder that when we study the cosmos, we are not just observing distant suns. We are witnessing the potential for new life, observing the echoes of cosmic death, and ultimately continuing our own search for our place within this vast and magnificent universe.